Friends, welcome to the last lesson of this lecture series on microprocessors. In this lesson, we shall discuss about the architecture of 16-bit microprocessors and then give a glimpse of the current trends. With the advancement of VLSI technology, it has been possible to integrate more and more transistors on a single silicon chip. Let us look at the graph. This graph shows the rapid rate at which the number of transistors per chip has increased over the years. This led to a very rapid evolution of microprocessors. You may recall the evolution tree that we have introduced in the last lesson. This tree has two main branches. We have discussed in detail about the right-hand side branch representing the microcomputers and microcontroller. In this lesson, we shall be concerned with the left-hand branch of the tree representing the powerful CPUs. In the last 2 decades, the CPU capability has broadened from 4-bit to very powerful 64-bit, incorporating many advanced features of the mainframe computers of 70s. The graph gives an idea about the rate at which the processing capability of microprocessor has grown over the years. First of all, I shall discuss the basic features of 16-bit microprocessors. The 16-bit microprocessors have powerful register organization with relatively large number of general purpose registers and special purpose registers compared to their 8-bit counterpart. Typical number of registers vary from 16 to 24. Address space. They support a large memory space. The address space size vary from few megabytes to several gigabytes, in contrast to only 64 kilobytes supported by most of the 8-bit microprocessors. Data types. They support wide variety of data types such as bits, bytes, words and long words in integer form, packed BCD and strings. A wide variety of addressing modes is supported, including register indirect with post decrement, post increment, displacement and indexing, stack, PC relative, etc. This facilitates implementation of high level language data structures very easily. Instruction set. Powerful instruction set providing multiply, divide, bit manipulation, string manipulation, etc. Pipelined architecture. Conventionally, a single CPU performs all the operations for instruction execution sequentially. Instead of that, different operations such as instruction fetch, instruction decode, operand fetch, ALU operation and write result can be performed by different units in an overlapped manner as illustrated in the diagram. Here, while the instruction fetch of instruction 2 is taking place, instruction decode of instruction 1 is going on. In this way, in the 5th cycle, write request of instruction 1, ALU operation of instruction 2, operand fetch of instruction 3, instruction decode of instruction 4 and instruction fetch of instruction 5 are taking place simultaneously. This kind of parallelism is known as pipelining, which have been incorporated in the architecture to improve throughput. Multiprogramming. The architecture of 16-bit microprocessors provide built-in architectural features to support multiprogramming. This allows several programs of different users to be resident in the computer's memory and execute them simultaneously in a time-shared manner. To support this feature, the microprocessor must have a large memory space and provide protection of one user's program from the others, controlled sharing of information amongst different users, and perform fast task switching. Multiprocessing support. To achieve high throughput, multiple processors can be used simultaneously to solve a given problem. To facilitate multiprocessing, several related problems such as process synchronization, inter-process communication, and bus contention ought to be resolved. Built-in architectural features are provided to resolve these problems. There are two basic approaches known as coprocessing and multiprocessing. In the first case, special purpose coprocessors such as IO processors and numeric processors have been designed to solve special purpose processing needs. This approach provides a powerful and flexible means of extending the basic instruction set and support new data types such as floating point operations. In the second case, multiple processors are used which share a common memory for information exchange. The sharing of common memory takes place through a common bus. As a result, at a time, only one processor has access to the shared bus. To avoid bus contention and facilitate inter-process communication, external bus arbiter hardware along with special purpose instructions have been made available in most of these 16-bit microprocessors. After considering the basic features of 16-bit microprocessors in general, let us now go into the details of the architecture of Intel 8086, the most popular 16-bit microprocessor. The number of pins used in this microprocessor is 40, and as a result it has used multiplexed bus architecture like 8085. The operating frequency of 8086 varies from 4 MHz to 8 MHz. I would like to mention that the processor used in the most popular computer, the IBM PC and PCXT system, is Intel 8088. This 8088 is functionally identical to 8086 except the external data bus is 8-bit and there are some other minor differences. 8086 architecture. Pipelining has been incorporated in 8086 by providing two independent processors called execution unit or EU and bus interface unit called BIU, allowing instruction fetch and execution operations in an overlapped manner. The BIU performs all bus operations and stores the fetched instructions in an internal RAM known as instruction queue of 6 byte size. The EU,
on the other hand, performs instruction decoding and execution by taking the prefetched instructions from the queue. This greatly enhances the program execution of 8086. Register organization. There are 14 user accessible registers in 8086. The first four, AX, BX, CX and DX, are meant for general purpose usage. Each of these 16-bit registers can also be accessed as two 8-bit registers. For example, AL and AH can be separately accessed. The four registers SP, BP, SI and DI belong to the pointer and index group. These are primarily used as memory pointers and index registers, although they can also participate in most of the arithmetic and logical operations. The next four registers CS, DS, SS and ES are called segment registers. These are used for flexible addressing. The 16-bit instruction pointer IP essentially perform the function of program counter. The last 16-bit register provides 16 1-bit status flags, of which 9 are active. Memory organization. 20-bit address bus allows up to 1 megabytes of memory to be accessed. The memory space of 1 megabytes is divided into logical segments of up to 64 kilobytes with direct accessibility of 4 segments at a time. The segment registers provide base address of these 4 segments as shown in the diagram. Physical address generation. A programmer logically represents a memory location by two entities, where one of the segment registers provide the base address and the other register supplies a 16-bit offset value. The BIU generates the 20-bit physical address by shifting the segment base value by 4-bit positions and adding the offset value as shown in the diagram. This process of address generation has the effect of dividing the 1 megabytes of memory space into a number of overlapping segments, each segment being 64 kilobytes long, begins at an address that is divisible by 16. Programs of different users can be stored in different segments of the memory, thereby creating an environment for multitasking or multiprogramming. Instruction set. The instruction set of 8086 not only includes the instruction set of 8085, but also provides a number of additional features and functions. Some of the significant operations and features are as follows: data types, bits, bytes, 16-bit words and 32-bit double words, packed BCD and unpacked BCD. Arithmetic operations: addition, subtraction, multiplication and division of signed and unsigned binary numbers, as well as unpacked BCD numbers are provided. String operations: move, scan and compare for strings of up to 64 kilobytes in length. Bit manipulation, bit testing in non-destructive manner, software interrupts, a large number of software interrupt instructions, multiprocessor support instructions, a number of special instructions to support the coordination of activities in a multiprocessor environment. Addressing modes. A variety of addressing modes are supported, including register indirect, register relative, best indexed and relative best indexed. The possible ways for the generation of physical address is shown in the diagram. This diagram shows the possible ways to calculate the effective address and a physical address for accessing data in memory with the help of different addressing modes. Multiprocessing support. The 8086 has built-in architectural features to support multiprocessing. It has two modes of operation known as minimum and maximum mode, realizable by strapping the MN/MX bar pin to VCC or ground. In the minimum mode, it can be used in a single processor environment, whereas in the maximum mode, the memory and I/O control signals are generated in coded form and an external device like 8288 generates these signals. In this mode, the hold and hold acknowledge lines are transformed into two sophisticated signals known as request/grant0 and request/grant1 lines. With the help of these lines, sharing of any common resource such as memory can be achieved between the 8086 and two other processors. Bus arbiter chip can also be used when the number of additional processors exceeds 2. The coprocessor wakes up and starts executing the instruction meant for it. It also deactivates the test bar pin of the host with the help of the busy pin. Whether the coprocessor has finished the instruction execution is sensed by the host through the test pin with the help of wait instruction. Some examples of other 16-bit microprocessors are shown here. Intel 80186, 80286 and 8088, Motorola 68000 family including 68100, Zilog 8000, Texas Instruments 9900. A list of commercial state-of-the-art high-performance 32-bit microprocessors is given here. Intel IAPX 432, 80386, 80486, Motorola 68020, National Semiconductors NS32032, Zilogs Z8000, HP's Focus, Western Electric's WE32032, NCR's NCR132, Dizzy's Micro and DEX Micro 1.
The category of microprocessors we have discussed so far can be considered as complex instruction set computers. After a critical study of the architecture of microprocessors and the instruction set, it was found that the complex instructions are rarely used. On the other hand, the infrequently used instructions are simple, and therefore, the infrequently used complex instructions can be removed and the frequently used instructions can be made to implement faster. Based on this motivation, a new class of microprocessors emerged known as reduced instruction set computer or RISC computer.
Some features of RISC microprocessors: a load and store architecture, that is, only load and store instructions access memory, while the rest of the instructions operate only on registers. A Harvard architecture with separate memories and data buses for data and instructions. Single cycle execution of most of the instructions. A fixed instruction format, a large register file, pipelined operation in fetch and execution operations, operating at 200 megahertz, providing throughput up to 400 MIPS. There are special purpose RISC processors. For example, digital signal processing microprocessors. These DSP chips can perform FIR filtering, fast Fourier transform, etc. as needed in real-time signal processing applications. These processors can perform addition, subtraction, multiplication, and shift operations with the help of special purpose functional elements such as hardware multiplier and barrel shifter at a very fast speed. Examples of these DSP processors are NEC's MuPD 7720, MuPD 7723, Texas Instruments TMS 320 and TMS 320C25. American Microsystems 28110, Motorola's DSP 56000, Analog Devices ADSP 2100. Another example of this special purpose RISC processors is the transputers. The InMOS transputer is a microprocessor which has been uniquely designed to function as a component processor in a network or array of multiple processors. A typical member of the transputer product family is a single VLSI chip containing processor, memory, and high-speed communication links which provide point-to-point connection between transputers. Transputers have been designed specifically to support multiple CPU fine-grained parallel processing. You will be very delighted to know that the indigenously available parallel processing system known as Param, developed by CDAC, is based on transputers. Friends, with this, the lecture series on microprocessors is coming to an end. But remember, this is the beginning for you. Just like swimming, to acquire the knowledge on microprocessors, you have to practice using microprocessor kits and develop microprocessor-based systems. I hope you have been benefited through this lecture series. Please send your feedback to us, and if there is any query, you send your letter addressed to Principal TTTI, Chandigarh. Thank you for being with us. Goodbye.